The captions you're seeing on screen right now were automatically transcribed from this video by IBM's 2 billion parameter Granite Speech model. As a matter of fact, not only were they transcribed, they were also automatically time-synced using the Granite model. But if you take a look at Granite Online, by default, it doesn't support time alignment. It only supports transcription and translation. So how did I do it? That's exactly what we're going to be diving into today. I'm going to give you a walkthrough of the experiment that I ran to extract this temporal alignment information from Granite Speech. But to start off, how was Granite Speech even trained? Well, in reality, Granite Speech is kind of a fusion of two different models along with the training of specialized adapters for them to work together. It starts off with a base chat-tuned Granite language model. This language model is used for the sort of core semantic understanding and the generation of the actual, language given audio. And then on the other hand is a special audio encoder model also trained by IBM Research. This audio encoder model is based off of a conformer architecture, and effectively the way that it works is it was trained independently on its own to actually perform ASR. So this conformer model was going to take in audio as a Mel spectrogram, and then it would output tokens. These tokens were then projected into a 42-character sort of classification space, which was trained with CTC loss. So CTC loss is a typical, very traditional loss function and training objective used for training ASR models. It's not particularly computationally efficient because of the way that the loss function works with respect to searching the output space. And then also specifically when sampling, it's also not very computationally efficient. And nowadays there are better ways of doing ASR, including what the Granite Speech architecture does. However, what this initial training phase did for the audio encoder was it trained a really, really strong model for encoding audio, specifically these slices of the spectrogram, into embeddings which contained a lot of rich semantics about what was contained within the audio. The semantics of the audio, we get really rich embeddings for them via this model. In particular, we get these outputs at 50 hertz. So every 1 second of audio gets converted to 50 of these embeddings generated by that initial audio encoder model. Given that information at 50 hertz, we then want to downsample it. So IBM also trained a very simple Q-former module, which would take non-overlapping windows of size 15 over these embeddings that were output by the audio encoder, and then sample them down to just 3 tokens. And so in total, if you take a look at the math there, you end up with a final sample rate of 10 hertz. So via that initial audio encoder and then this Q-former block, we're able to reduce our audio to 10 embeddings for every 1 second of audio. These 10 embeddings per second of audio are then fed into the Granite model, which is then run inference on using a specialized LoRa adapter. This LoRa adapter is what enables Granite to sort of understand these speech tokens, and then from there, we're good to go. Granite's able to generate audio rather generate transcripts or translations via understanding these audio tokens with this LoRa adapter applied. It really is some fascinating technology that goes behind the Granite Speech architecture, but one of the fun things about training models like this is that internally they'll oftentimes learn more than what you explicitly give them a training objective for. My favorite example of this is OpenAI's unsupervised sentiment neuron research from back in 2017, where they realized that training a simple character-level LSTM model to generate Amazon reviews actually resulted in its very final layer learning a single linear representation of the concept of sentiment, despite that never having been an explicit training objective. It just learned it because it was useful for the operations at hand. And so, similarly, when you take a look at models like Granite Speech or Whisper or other ASR models, oftentimes they'll learn other useful information internally that we can extract later despite never being trained to do so. That includes temporal alignment. A couple months, maybe even years ago at this point, some researchers and some folks in the community found out that if you take a look at the cross attentions between OpenAI's encoder, which is what encodes audio information, and its decoder, which is what then generates text, you can actually find specific attention heads that have a certain monotonicity to them. They have a certain tendency to sort of keep the text attentions aligned to where in the audio that text actually corresponds to, or where in the audio that text was actually being verbalized. And I thought, of course, it would be really interesting to see if Granite Speech had similar attention heads. So here's what I did. I started off by writing a script that would allow us to perform inference against Granite Speech, generating transcriptions with just one sort of special hook. This special hook allows us to extract a visualization of every single attention head in every single layer of the Granite model. This, of course, generates a lot of visualizations. For one inference pass, you get something like 1,200-ish visualizations from Granite, so it's a lot of data to go through. But I think it's a really interesting set of visualizations. For example, what I did is I passed in a very simple audio clip, a typical example, with audio saying, "The quick brown fox jumps over the lazy dog." And after feeding it into Granite and generating these visualizations, I could show you a couple of these visualizations on screen right now, and you'll notice that what it's representing is for every text token in the transcript on this y-axis, right? So starting with the very first text token at the bottom of the y-axis, going up to the final text tokens, versus on the x-axis, all of the audio tokens that represent the audio in. You can sort of see the attention matrix, the activations in the attention matrices, showing us where these heads are taking information from the audio tokens and placing them in these text tokens. One of the things you might notice if you really pay attention to these diagrams, by the way, is that if you were to sum across the rows, to sort of see if they sum to 1, you'll notice the answer is actually no. So it seems like there's some missing information here, or that I've done something weird with the attention matrices, but actually, this is correct. It's just that, remember, there are other tokens in the prompt, for example, and also the start of the assistant header token and the end of the user turn and so on. There are other tokens here that are not depicted in this attention matrix visualization, that's why they don't sum to 1. But still, it's sort of interesting to see when we scope it down to this level, what sorts of patterns, or, for most of these heads, lack thereof, there are to how they activate. You'll notice that some of them almost seem like they have some sort of cyclic nature to them. That might be because of potentially rotary positional encoding, whatever the reason is. Point is, these different heads have different patterns of activation, and for a lot of them, they're not necessarily intelligible. I can't tell you what it is that these heads are informing the model of, or teaching the model. But then, here's the interesting thing. The sort of pattern we're looking for, which is that as text tokens go, up in the temporal dimension, as text tokens move forward, they attend to later and later audio tokens more and more locally, right? So the density of their activations is higher, and it's towards future audio tokens. That pattern can be described mathematically. And so what I can do is I can write a very simple function, and this function ranks an attention head based off of how monotonous that activation is. And so, after having ranked them all, we actually find some with some insanely high scores that really give us an indication that they do have this sort of correlation between the text and audio's temporal axes. So let's take a look at them. In particular, for the sample that I tested just now, so the quick brown fox jumps over the lazy dog, we find that on layer 16, head 23 is the one with the highest score. So if we take a look at the visualization for that head, you can actually see the sort of pattern I was talking about. So as we go up on that y-axis, we move to the right on the x-axis. So later text tokens attend to later audio tokens. Now, I haven't precisely done the math to see if those specific audio tokens would correspond to those particular segments of audio. However, given this pattern, it's reasonable to assume that because of the semantics being described by the data, that the model would want to learn that kind of alignment because it helps it realize sort of what to pay attention to, literally, when it's figuring out how to transcribe. You'll also notice that the attention weights are a lot higher here than in some of the other random matrices, because now we're sort of really getting to the heads that are focusing on this task. There are, of course, some other heads, like, for example, layer 34's head 5 and head 29 also had very high scores, as well as layer 33's head 21, 34's head 6, and 31's head 20. So there are quite a few different heads that learn this kind of pattern. But what you may have noticed as I show you these different visualizations is that they all learn slightly different representations, right? They have slightly different activations. Some of them are a bit more noisy. They're not quite as high of a score with respect to monotonicity. And so they represent slightly different pieces of information. And so here was my thought. Well, what if we could take the information from across these different attention heads and then train another very small model, purpose-built just for the task, of taking an individual one of these rows across all the attention heads and then predicting the start time of a word. And that is exactly what I did. So next step for me was to take the LibreSpeech ASR corpus, which is a pretty large data set used for training ASR models and testing ASR models. And it has one really neat piece of data that we're going to want here. It has word-level alignments to its transcripts. So it has audio files, it has transcripts, and then alignments of exactly where in the audio individual words started being spoken. So what I did is I took a bunch of those audio files, fed them through Granite Speech, did a raw data dump to NumPy files of all the different attention matrices from all the heads for each file, and then, across all of them, chose the top 10 heads that had the highest scores of how likely they were to have that correlation of future text tokens attend more to future audio tokens. After collecting that set of heads, I went ahead and collected all the data from those heads for the individual tokens that represented the starts of words, and then trained the model. After training the model, we now have one that's capable of taking any one of these rows from the attention matrices and predicting the start time of words. In particular, the way that it works is we take all the different audio tokens, attention matrix values for all 10, right? So for example, for an individual audio token, we'd have a 10 sort of dimensional feature vector that we feed as input, one feature for each head. We project that into a 256 dimensional space. That is then treated as a token, along with all the other audio tokens projections, as input to a different transformer model that I've trained. This is a very simple, relatively shallow transformer model, just 8 heads, 4 layers, 256 dimensionality, trained with pre-norm and rotary positional encodings. This model will then project these and sort of like process these tokens generated by the attention matrices. And given that final data, we then project the resulting tokens into just scalar values. Then across all the quote-unquote audio tokens, we then compute softmax. And then for each audio token, we know how much of a stride there is in the audio input pre-processing logic before feeding into Granite. And in this case, it's 0.1 seconds, so 100 milliseconds is sort of like our stride time. So then we simply assign those stride indices to each output index from the model, and then we use the softmax weights to compute a final weighted average of where in the audio we believe the word would have started, and we use that versus the target time we know from the LibreSpeech corpus, optimized with mean squared error to finally give us a model that's capable of predicting start times given the activations from the attention matrices within Granite Speech. And I'm glad to say that the model actually works incredibly well. And that is a really interesting way of demonstrating how you can be really creative with machine learning models. It's not just about using them what they were trained for. You can actually extract a lot more knowledge, a lot more information, a lot more use out of them just by taking a look at the internals and hypothesizing about what they may have learned and how you might be able to extract that information for yourself. Of course, all the code will be available down in the description below for you to go ahead and run and try this out yourself. And of course, feel free to try this out on the larger 8 billion parameter Granite Speech model as well. I'm very curious to see what you might find or if the result might be better. Now, Granite Speech has a different audio input encoding scheme than models like OpenAI Whisper, which does make this a little bit more difficult to perform this kind of temporal alignment, but I'm sure there's ways that this could be made even more precise. It's a really powerful model, so I'm sure the information's in there somewhere. It's going to take some experimentation to find it. But with that, thank you very much for joining today. I really hope you enjoyed that. If you did, please do make sure to leave a like down below and leave a comment if you have any questions, suggestions, or feedback. I would love to hear from you, or reach out to me on my social media or email. Apart from that, if you enjoy this kind of content, you want to see more of it, please do make sure to subscribe to the channel, as it really does help out a lot, and turn on notifications so you don't miss it when I release videos like this one today. With that, thank you for joining. Goodbye.